Buenos días a todos los que estamos aquí y todos los que estén viendo ahora además el video. Tengo el honor y el placer de presentar al profesor doctor Paolo Mancosu, profesor en la Universidad de California en Berkeley. Paolo ya ha venido varias veces a Buenos Aires. Es un placer tenerlo ahora en este workshop de filosofía de la matemática organizado conjuntamente por el CIESE y por el IEP. Paolo es posiblemente uno de los más importantes filósofos de la matemática en la actualidad. Me gustaría mencionar que en el caso de Paolo se conjugan desde el punto de vista meramente formal, sobre todo formal y matemático, al analizar los problemas de la filosofía de la matemática con aspectos históricos, siguiendo una tradición interesante, o sea, uniendo tradiciones más analíticas y focalizando además en la historia y en la práctica matemática. Paolo tiene una larga serie de publicaciones, de artículos y libros, pero me gustaría mencionar solamente dos que han sido muy importantes para la filosofía de la matemática más reciente. Él publicó un libro sobre fundamentos y práctica de la matemática en el siglo XVII, que tuvo mucha repercusión y que inició prácticamente en el momento una nueva línea, y además publicó una colección de trabajos sobre esa nueva corriente muy importante en la actualidad, que es filosofía de la práctica matemática, Philosophy of Mathematical Practice, y él se cuenta entre los iniciadores de ese punto de vista, de esa perspectiva, que busca analizar las cuestiones filosóficas de la matemática en vinculación precisamente con la práctica que tienen los matemáticos o de otras disciplinas, ¿no? Con lo cual se vuelve una tarea muy interdisciplinaria. Bueno, Paolo, es nuevamente un placer tenerte aquí. Él va a hablar en inglés. Lo he presentado en español porque él habla español. Three Applications of Zermelo's Theorem or Pan-Hole, y es un trabajo que tiene que ver con varios artículos recientes que él ha publicado. Bueno, Paolo.
Gracias, muchas gracias, Javier. Es siempre un gustazo volver a Buenos Aires, y lo que quiero hacer después de esta introducción en castellano es presentar tres artículos recién sobre el tema de aplicaciones de un teorema de Zermelo que voy a describir a la cuestión arte-todo, que es una cuestión fundamental en la historia del infinito, desde los griegos hasta hoy. Tenemos una hora y media, entonces porque el tema está bastante técnico, pero lo que intento hacer es dar las líneas esenciales para comprender la arquitectura de este tipo de trabajo sin entrar demasiado en los detalles. Las pruebas, los artículos están publicados de toda manera, no hay problema si uno está interesado a mirar las demostraciones. Okay, so I will now switch to English, and let me start giving you an overview of what this contains. I'm gonna give you a general introduction on this theorem by Zermelo, and I will say more about it. And then we're gonna look at three areas of application of this result. One is issues in neologicism and inconsistent abstraction principles. Another one is applications to the formal studies of the axiom of choice in second-order logic. And finally, issues in probability theory having to do with a notion called regularity, which I will explain when we get there. And finally, I'll give you some. Okay, so let me just skip here. Here are the 3 articles that I will mention. One is the first one from 2019. It came out in the proceedings of the Wittgenstein Symposium in Kirchberg. And that's the one that is connected to neologicism. The second article is, it's just come out in the Review of Symbolic Logic in 2023, and it's written with Stuart Shapiro and Benjamin Siskind. And finally, there is a new one that just came out online for philosophy of science, and that's the one having to do with probability theory. What is common to all the 3 articles is the exploitation of a result by Ernst Zermelo to situations in which the relation of strict subset inclusion, which I call part-whole, is of relevance. Now, if you look in the literature for Zermelo's axiom, you won't find this theorem, or Zermelo's theorem. You will not find it described in this way. And I will tell you the reasons why. Because this theorem, in effect, was implicit in the very famous article that Zermelo wrote in 1904 on the equivalence between the axiom of choice and the well-ordering theorem, property that every set can be well-ordered. In the midst of proving this equivalence, Zermelo does something that Kanamori in 1997 brought out from that paper. And so it's a result by Zermelo, so to speak, but you won't find it stated as a theorem or anything of that sort. Here it is. It's a wonderful result because of the simplicity of the statement and the generality of the statement itself. It says the following. Take an arbitrary set X, look at the full power set of X. Then, given any function, any, no restrictions, from the power set of X into X, you're always going to find 2 sets in the power set, which the function sends to the same value, and have the property that one is strictly included in the other. So in other words, no function from the full power set of the set into a set manages to track the relationship of strict subset inclusion. If you try to have a function that preserves strict subset inclusion by giving different values to sets that are in that relation, you will fail, because the function is going to fail on at least 2 sets that are in the strict subset inclusion. So, very simple example. Take any function from the power set of the natural numbers into the natural numbers. There is always going to be 2 sets of natural numbers, one included in the other, strictly included, that the function will sense exactly to the same natural number. Now, how do you prove this theorem? Well, it's easy to prove it by a transfinite induction. Basically, you start constructing the 2 sets that will defeat the attempt to preserve part-whole. But the important thing for us is that transfinite induction is something that you have available in set theory. When you move to other contexts, like pure second-order logic, transfinite induction is not there. You don't have the set theory available in second-order logic, which means that you have to get around your expressive resources in order to regain the result in other ways. That's the real difficulty of the thing. Okay, here is the transfinite induction in a nutshell. So you have this function that takes you from the power set of a set to the set itself. You start by looking at what the function does as the empty set, because the empty set is one of the subsets. Well, the function will give a value to the empty set. You start collecting that value into a singleton. Then you ask, what does the function do to that singleton? That's also a subset. And so it will have another value. If it is the same value that it was given, that the function was given to the empty set, you're done. You have found the two sets that defeat part-whole assignment. If not, you keep going. Now you look at the value that you get applying the function to the singleton of the x0, and that's going to give you this f of x0, which either is going to be, sorry, I'm just going to put, yeah. So otherwise f0 is some x1, which is not in that singleton. And so then we put this x1 in the set you're constructing B. Now what is the transfinite induction? Transfinite induction is that at the end of this process, right, this is very vague, but the point is that because you're dealing with a set, eventually you will run out of elements. At the end of this process, you're going to get some well-ordered set B such that for all proper initial segments Z of this set B, f of Z is the next element in the well-ordered you're constructing. But then, you know, once you have constructed this B, f of B must be in B. Why? Because the process must come to an end. You run out of elements. But how did this f of B get in B? Well, f of B got into B by being the f value of some proper initial segment A of the set B. So of a subset of B. And so you have found your B and A, which have the same value, but where A is strictly included in B. So this is a theoretic argument. Of course, it's very fast, because I don't want to get into the reconstruction, the details, but the point is simply that you get to a fixed point of this construction. But none of this is available in second-order logic, because that's, you know, that requires transfinite induction in set theory. When you're dealing with Frege systems in second-order logic, which have second-order logic as background, or pure systems of second-order logic, this stuff is not there. So what do we do? Well, let me tell you something before we get to the technical results about a program that has been absolutely central in philosophy of mathematics in the last 50 years. That's the program of neologicism, which emerges in the contemporary debate in philosophy of mathematics with a book by Crispin Wright called Frege's Conception of Numbers as Objects, published in 1983. Now, Wright's project was to show the viability of a philosophy of mathematics that could preserve the key tenets of Frege's approach. Now, prima facie, this might have seemed like an impossible task, because after all, Frege's foundational system, which was first presented in the Foundations of Arithmetic and in later formulations in the basic laws of arithmetic, relied on the use of extensions of constants, defined or codified by means of the infamous Basic Law 5. And we know that Basic Law 5 engendered the contradiction of the system, and Russell proved this in 1902. Now, what does Basic Law 5 say? Basic Law 5 postulates the existence of a function delta that maps the concepts into the objects of the domain. Right? The system in Frege is, you have basically two types of entities. You have concepts and you have objects. For the purposes of this talk, you can, without any loss, think of concepts extensionally as subsets of the domain. So there are, if I have a domain of objects, the concept reg is just going to be extension of that set of reg things on that domain. And this function maps every concept into an object of the domain according to a very simple principle. That if you have two concepts, x and y, the function delta will give them the same value if and only if the two concepts are equi-extensional. It's a very simple thought in a way. So if you have the concept of being triangular and being equilateral applied to triangles, that function will give those two concepts exactly the same extension, because all equilateral triangles will be also equiangular. Now, it's easy to show that basic law 5 entails an unrestricted comprehension axiom, meaning a set existence axiom for any property whatsoever. And so what Russell did was to show that you can't have this kind of unrestricted principle, because when you apply it to x does not belong to x, you get a contradiction. People tried to find a solution, making little changes to basic law 5, but they really didn't manage. So for about 80 years, people thought that Frege's project, however beautiful it was, could not be salvaged, really. I mean, of course, there was the logicism of Russell, but it required such modifications that it really didn't quite look like the Fregean one. Now, Wright's approach, the attempt to revamp the Fregean foundational program, emerged as a combination of a powerful technical result and a host of philosophical arguments. I will tell you that there is no debate about the technical result. The technical result is super solid, and the problem is not there. Of course, once it gets to the philosophical arguments, there has been 50 years of discussion on this stuff. So what Frege does in the foundations of arithmetic is it uses extensions of concepts to gain an intermediate result, which is called Hume's principle. And it's called Hume's principle because Frege mentions Hume at that point. And Hume's principle is something very similar in a way to basic law 5, because it's a way to abstract a function from an equivalence relation among concepts. In basic law 5, the equivalence relation is equi-extensionality, and you get then an abstraction of a function which gives you the extensions. Here, the equivalence relation is this thing that we abbreviate as a squiggle. It's something that can be defined in pure second order logic, and it says that everything that falls under X can be put in one-to-one correspondence with everything that falls under Y. So it's really the Cantorian notion of cardinality. There is a one-to-one correspondence between the objects that fall under X and Y. And if you abstract, you get a function which is called the number of. Just as Cantor was assigning cardinal numbers using that equivalence relation, Frege does the same. Reaches this point in the development where he assigns the number of concepts in this way. So here is the logical structure of what Frege does. He first needs extensions of concepts to define explicitly this function number of. So that function number of is defined explicitly by Frege in terms of extensions of concepts. Once he gets there, once he gets this law, he goes on to derive the axioms of second order arithmetic in second order logic. He never uses in that derivation the basic law 5 or extensions of concepts. So the idea is that extensions of concepts are only needed to get to Hume's principle. once you reach Hume's principle, you go from there to deriving the basic laws of arithmetic without appealing to concepts. So Wright's great thought was, well, why don't we start from Hume's principle and second order logic, and then claim technically, that we can derive from Hume's principle and second order logic the axioms of arithmetic, and then argue philosophically that Hume's principle is a good starting point for a Fregean philosophy of mathematics, meaning that it has all the epistemological virtues that the logicist project would require. So something in the vicinity of being a definition or being analytic in some sense. So not too far, at least, from logic as Frege might have understood it. Okay, so I hope that what Hume's principle says is clear. It simply says that the number of two concepts is the same if the objects that fall under the two concepts have exactly the same number, are in one-to-one correspondence with one another, right? So the famous example of a well-set table by a waiter tells you that you don't need to count the forks and the knives, because you can make sure that for the concept fork on that table and for the concept knife on that table, the objects that fall under them are in one-to-one correspondence. So the result, the technical result I was mentioning, is expressed by this little formula down here, which is Frege arithmetic proves syntactically that the axioms of second-order piano arithmetic. So what is Frege arithmetic? Once again, it's a system of second-order logic as we understand it, plus Hume's principle. And just from those two things, and of course definitions that you will need to introduce zero successor and so on, you can get the axioms of second-order arithmetic. Now, this type of discussion has led to the detailed scrutiny of what are called abstraction principles, of which basic law 5 and Hume's principle are the most famous instances. Indeed, one of the first objections to the proposal that Wright was making, that accepting Hume's principle was fine, was an argument which is the very first form of what are called bad company arguments, saying that, look, basic law 5 doesn't look very different, definitionally, so to speak, than Hume's principle. After all, what are we doing? We're taking an equivalence relation on concepts, abstracting a function out of that preserves the equivalence relation. But basic law 5 looked innocuous and got us into contradiction. So how do we know that Hume's principle is not going to do the same? Okay, first move in retort to that is, well, there is a difference, because basic law 5 is demonstrably inconsistent, and Hume's principle can be shown to be equivalent to second-order piano arithmetic. In other words, second-order logic plus Hume's principle, this system of Frege arithmetic, turns out to be equiconsistent with a second-order piano arithmetic. And since nobody in their right mind thinks that second-order piano arithmetic is inconsistent, that gives, as it were, credibility to Hume's principle. But this was only the first of a huge literature on bad company objections. And I'm not going to go through them. This was just to give you a sense of the beginning of this debate. Now, until I started working on this topic, basic law 5 was the only example of an abstraction principle that led to contradiction. And so it seemed like it was some kind of monster in otherwise a universe of acceptable abstraction principles, and that something, went wrong for this particular isolated case. So it seems like a real exception in an otherwise unpathological landscape. And the use of Zermelo's theorem that I want to discuss with you shows that, in fact, basic law 5 is no monster. It's an instance of a much wider set of abstraction principles that all share one important property. So, let me summarize again what abstraction principles do. Abstraction principles in this Freudian context compress, if you want, the concepts into the objects according to an equivalence relation on concepts. If one look at the situation set theoretically, in other words, if you think of concepts as their extensions in the domain, this corresponds to the idea of mapping the full power set of a set X into the domain X itself, according to an equivalence relation that we have defined among the elements in the power set. Now, in the case of basic law 5, this relation is the extensional identity of the sets. In the case of Hume's principle, is the existence of a one-to-one mapping between the elements that fall under one concept and those that fall under the other concept. So we can express this more formally as the request that we have a function delta such that delta x equals delta y if and only if x, e, y, where that e is some equivalence relation on concepts. Now, what does it mean to say, and now I'm getting close to Zermelo's theorem, what does it mean to say that delta satisfies a part-whole constraint? It means that an abstraction principle or function that is defined in the abstraction principle satisfies part-whole, meaning that if we have such an abstraction operator, we might ask whether this property part-whole is satisfied. What does it say? It says, for every concept x and y, if x is strictly included in y, then I can keep track of that by giving them different values. Okay? That's what part-whole says. Where, of course, all of this stuff can be defined in pure second-order logic. That's the definition of strict inclusion, for instance. But now, here is the thing. No Freudian model can satisfy this property. What's a Freudian model? It's a triple, which is the universe, the full power set of that universe, and a function f that sends the power set of x into x. But by Zermelo's theorem, we know that for any set x and any function f, if f is sending the full power set into the domain, part-whole has got to fail somewhere. So we're going to have this delta, which, despite the fact that a is strictly included in b, will assign them exactly the same value. Now, so semantically speaking, you're not going to get a model of an abstraction principle that satisfies part-whole. But we are in second-order logic. Second-order logic, because of Gödel's incompleteness theorems, tells you that you might be in a situation where you have no models, and yet you might have a consistent syntactic system. So one from which you cannot derive a contradiction, syntactically speaking. That's a more difficult problem to solve. So we have no models, there are no interpretations that satisfy this thing, but if I do postulate a function of this sort, satisfying part-whole, am I going to be able to derive the way Russell did, syntactically, an explicit contradiction? As I said, I'm not going to go through the details because the purpose of this talk is to give you a sense of the architecture of the projects. But in fact, it turns out that by appropriately redefining things, and it takes 3 pages of hard work, you can, in pure second-order logic, only with the addition of a name for a function that sets from the power set into x, because you need to mention that, you can change everything so that you can show that in pure second-order logic, you can syntactically derive that the postulation of a function delta that preserves part whole in that way is going to lead to a contradiction. Okay? So we move from the semantical level where we know there was no model to an explicit syntactic contradiction for any such property. Well, obviously, BL5 is the first victim of such a reason, because BL5 was, in fact, the way it is defined has to preserve the subset, the part-whole principle, right? If 2 sets are extensionally different because one is a subset of the other, then if we had a function satisfying part-whole, it would have to give them different values, okay? And it doesn't do that because it gets into, in fact, a contradiction, as we prove in this general result. So we gain back a result that was well known. Now, this would be of not great importance. Now, okay, you got Russell's paradox back. It becomes interesting if you can show that there are infinitely many different abstraction principles that are all subject to the same argument. And that is, in fact, what we do with a former student of mine, Benjamin Siskind, where we show that if delta respects part whole, sorry, this is just a summary of what I said about BL5, so let me go to the next one. And this shows that, in fact, in pure second-order logic, you can prove, plus the symbol for a function that does what the abstraction does in the case of basic law 5, you can show that you get a contradiction. So this particular result, the way I stated it, is general. It says that in pure second-order logic, plus an additional symbol for any function that stands from the power set of the domain into the domain, you can prove that part whole has to fail. So second-order logic proves that for you. So now the question is that this is not only going to apply to basic law 5, it's going to apply to any other abstraction principle that satisfies part whole. So the final point is, well, are there others? And the answer is yes, there are infinitely many. There are as many as you could possibly ask for from the point of view of the cardinality of the language that you're dealing with. And I'm not giving the examples here, but they're not too difficult to concoct. You basically play around with these equivalence relations where you pluck out one number and you make it kind of an exception, and you can construct infinitely many of them pretty easily. So that's not the important thing. The important thing, which I want to bring home, is that Russell's paradox is only one instance of a much wider phenomenon. And so it's not some kind of isolated monster. Inconsistent abstraction principles exist galore in great quantity. And one of the things that joins them is that they all satisfy, in this family, is that part whole is satisfied by them. Now you might ask, which is what I was hoping for at the beginning of this work, whether in fact respecting part whole is the real essence of the paradoxical phenomenon that Russell had seen. In other words, you may ask not only if every abstraction principle that satisfies part whole is inconsistent. That answer is yes. But it's every inconsistent abstraction principle, one that satisfies part whole, and unfortunately, at least for my original goals, the answer to that is no. So there will be, and there are, we know them, other types of abstraction principles, and they're different from Russell's, they're different from the ones I'm describing here, that satisfy inconsistency, so they will give rise to an inconsistency, but they're not satisfying the property of part whole. Okay? So that's the first application of this stuff. So it's a massive generalization of Russell's theorem. That's what we have. Okay, I'm going to go a little faster on the applications of second-order logic because I want to get to the probability material. In effect, the applications of second-order logic to second-order logic rely only on a small modification of the key theorem that we use to show that you could get around the transfinite induction and prove Zermelo's theorem on part whole in pure second-order logic. With some small modifications of that, you can apply it to the study of various formulations of the axiom of choice in second-order logic. And that's a very delicate enterprise because in second-order logic, you can't even express the axiom of choice in the original form. Because if you recall the way the axiom of choice was stated by Zermelo, it requires what are called type 2-1 functions, meaning functions that take elements of the power set into the domain of the set itself. Right? Remember, the axiom of choice says if you have a sequence of sets, and those are coming from their subsets of the original domain, there is a function that picks an element for each one of them. So you need these functions that operates on subsets of the original domain. And what you want to state is for every set X, right, there is a covariant function, this is the technical terminology that Zermelo used, for X, if and only if X can be well ordered. Now, whereas well ordering, it's something that you can express in pure second-order logic. It's a property that you can define in pure second-order logic. This one of a covariant function for X forces you to go up in type. So what we do in this article in 2023 is to find an intermediate level where we don't state the full theorem, which would require you to work in third-order logic, but find an intermediate level which is similar to the one that the neologicist uses when it simply postulates the existence of an extra function, number of, that takes you from concepts to objects. And so we ask the question, if we extend our second-order logic with just one function that is going to act like a choice function, what can we say about this? Let me just give you the result. So if you have this extra function, you can define an axiom called choice that says the following. Take any concept X. If that concept is non-empty, in other words, if there is something that falls under it, then delta works on that concept and it gives you an element that falls under that concept itself. Okay, so that's choice. Any arbitrary set you have, delta works on it and tells you here is a representative of that set. So here is what happens. These are the two important results. That if you have second order logic extended only with this symbol for delta, for an extra function, and you assume choice, then you can derive the well-ordering principle out of that. And this is the important thing. In a sense, this theorem 3.2 says this is the best thing you could possibly do. In fact, this says that if you have second order logic plus this function delta, and you assume choice, then the results you get in the language that doesn't have the delta are exactly the same that you would get by assuming SOL plus the well-ordering principle. And remember, well-ordering principle is something that can be stated in second-order logic. It doesn't require any extra symbolism. So what's the essence of this? The essence of this is that in pure second-order logic, the statement of well-ordering is the strongest possible choice principle you're ever going to get. Because you can't prove the equivalence with the Zermelo's covering lemma, because that would take you to third order. You can't state that. But you can state the well-ordering principle, and this is telling you that the force of that well-ordering principle with respect to the original language is as good as having on board the choice principle in the Zermelo style, because you will be in a situation in which if you prove anything in the old language, in this system augmented with the choice principle, Zermelo style, well, that won't take you beyond what you could already prove with the well-ordering principle in the first place. Okay, so, and now to the third application in probability theory. I'll give you some refresher on probability spaces. I will define what it means to be regular, what it means to be total, and then we're going to get to see something interesting. So in the standard Kolmogorov approach to probability theory on infinite sample spaces, we have that these spaces are neither regular nor total, and I will define exactly what this means. In Kolmogorov probability theory, a probability space is just a triple. It's a triple omega, a collection of subsets of omega called B, and a measure mu. So omega is called a sample space, B is a sigma algebra of subsets of omega, and mu is a probability measure that assigns a real number in the interval 0, 1 to every set in B. So that's the general setup of a Kolmogorov space. Notice that in Kolmogorov's theory, there is always only one range for any probability function. It's the interval 0, 1. That's the way you do probability when you take ordinary courses in probability theory. What is regularity? Regularity, expressed set theoretically, is the request that only logical contradictions, that is, the empty set, get assigned probability 0. It is often understood as a bridge principle between modality and probability, in the sense that no possible event can be assigned probability 0. And this is a very natural intuition we have. Totality, on the other hand, requires that every subset of the sample space omega must be measurable, must be assigned a probability value. So before I move on, this is the most important slide in a way, because if you get these things and the kind of consequences that they have, you will see the importance of the work. So let me spend a few more times on that. These two properties do not hold in most cases that have to do with Kolmogorov probability theory. Consider the case of throwing darts at the interval 0, 1. Right? So I have a perfectly pointed dart, I have my 0, 1 interval, I never miss, I always land on the interval. What's the probability that I get 1/2? 0. That's Kolmogorov's probability theory. Very unintuitive, right? The probability of picking any single number in that interval is 0, and yet the interval has probability 1. That doesn't look that great in certain, at least, certain intuitions. So regularity is going to be the request that you should satisfy the property that no possible event, and surely, right, picking some singleton in the interval 0, 1 is a possible event. After all, when I throw my dart, it's going to land somewhere. So each one of those singletons should be possible events, and yet they get probability 0 in Kolmogorov. So the regularity request is that no possible event gets probability 0. So, of course, as I said, in the probability, in the Kolmogorov context, this fails. Regularity fails. Totality also fails, and this is a consequence of theorems in real analysis. In particular, the axiom of choice allowed to show that there are non-measurable subsets of the real line. That's a theorem by Vitali, which shows that there are subsets of the real line which cannot be assigned a probability measure. So you have to work with, for instance, the set of measurable sets in the Lebesgue sense. So, from the point of view of the classical definition of probability, it seems almost a triviality that any event with probability 0 cannot occur. When I refer to the classical definition of probability, it's the definition given by Laplace that gives you a ratio between the total number of cases and the favorable cases. From that point of view, it seems almost a triviality that you shouldn't get a probability 0 for a possible event. And this intuition, as I said, is reflected in what is called regularity. Now, things change dramatically with the application of measure theory to probability theory at the turn of the 20th century. Foreshadowed by Poincaré, who simply asserted that the probability of the rationals in the interval 0, 1 is 0, and by work on fractions related to astronomy, the idea that there are non-empty, even uncountable sets of probability 0 enters the probabilistic arena with Borel's development of the notion of Borel measure and the application of Lebesgue measure to probability theory. Now, Borel is very interesting from this point of view because we can read in his early articles this kind of split emerging. So I want to give you some quotes. Here is from an article written in 1909 by Borel, where he's contrasting discrete probabilities with what he calls two other families, the numerable and continuous probabilities. Now, this notion of the numerable probability was one of the big projects that Borel had. It never really went anywhere, but it was the idea of doing probability on countable domains. But it treats countable and continuous probabilities together. So the opposition we're interested in is the discrete case and the countable continuous. Here's what he says. There is a true discontinuity between an infinitely small probability, that is a variable probability that tends towards 0, and a probability that is equal to 0. Indeed, no matter how small the probability of the favorable case is, this is nonetheless possible. You hear here the regularity pool. Whereas it is impossible if the probability is 0. And now he adds, such are anyway the results, the classical results of discrete probability theory. In other words, classical probability theory on the discrete pulls you in the direction of satisfying regularity. But one knows that things are otherwise in the theory of continuous probabilities. The probability that a number chosen at random is rational is 0. This does not mean that there are no rational numbers. Things will be the same in the case of the numeral probabilities. Probability 0 should not be considered as the equivalent of impossibility. So, in other words, what contemporary probability theory does in its Kolmogorovian version is to pull apart possibility and probability. You can have probability 0 and yet be possible. And yet, that thought seems weird to us. If something is possible, then it's got some chance of occurring, right? So its probability should not be 0. And the story I'm telling you today is no different from another story I could tell you about Cantorian cardinalities. We got so used to a certain approach to probability theory that it has become dogma almost. That it's hard to think outside that box and start thinking, wait, maybe there is another way to do things so that you can preserve regularity even in these cases where classical probability, Kolmogorov style, tells you no, that the probability ought to be 0. In other words, why can't I have a probability theory where when I throw a dart at 0, 1, the probability of each point to be hit is different from value 0? That's the question to ask, mathematically speaking. From this point on, this distinction between probability 0 and impossibility becomes an accepted fact of continuous probability. Here is Hausdorff in that beautiful classic book on set theory from 1914. He says, it is also perfectly clear that from this definition, probability 0 is not the expression of impossibility, and probability 1 not that of certainty. For 0 is the probability that a point belongs to a set of 0 measure, which might be still of the cardinality of the continuum. Okay, so a few formal slides to set up. So this is a classical setup for a Kolmogorov probability theory. You have a triple omega, B, mu. You want to satisfy the following axiom. The probability of the entire sample space is 1. The probability of any set in your collection of sets B is greater than or equal to 0. And finally, you have countable additivity, meaning that if you have a family of pairwise disjoint sets, the measure of the union of those sets is the sum of their measures. So here are the two requests we're worrying about. Regularity, what would it mean? It means that if mu of A for a set A in B gets 0, then it's got to be the empty set. That's regularity. And mu is total if in fact the collection of sets B happens to be the entire power set of the sample space. Now, it's well known that, as I said, if we let, for instance, omega equals 0, 1, we witness in Kolmogorov setup both a failure of regularity and totality for many standard Kolmogorov probability functions. In fact, suppose you want a uniform probability function mu that is defined on all the singletons of the interval 0, 1. Uniform means that each singleton should count the same. Why should you give more to one than to the other? Well, an easy argument shows that, in fact, each one of those singletons should get measure 0 in this setup. And I've already told you what is the unpalatable consequence of this, that it just goes against intuition to really say that no point on the 0-1 interval has probability greater than 0 to be hit. Now, the failure of totality, as I mentioned already, also follows in the case of the standard set up with the real numbers by Vitalis' theorem, which says that there are non-Lebesgue measurable subsets of the real line, and so you cannot hope to have a full a probability function, which is which has the standard properties of probability in that setup. Now, if you don't require, as you do when you use Lebesgue measure, that the probability be translation invariant, what does that mean? If you have two segments of the real numbers, two intervals, and they have the same length, translation invariance means that the probability of those two intervals should be the same. If you don't make that request, then you could have total probability measures on the interval 0, 1. But those results is either you get something really trivial, or postulating such things is so hard, it's so demanding, so to speak, on the set theory, that the axioms that would justify the existence of such things cannot even be proved in Zermelo with choice. Now, the failure of regularity and totality raises the issues of whether there are connections between regularity and totality that one can describe in more general ways. I'm going to skip to some of that. And the importance of this discussion for philosophy is that this stuff about regularity has been revitalized in recent discussions in philosophy, not only philosophy of mathematics, I'm talking about epistemology in particular, issues of credences, and also by the emergence of powerful infinitesimalist approaches in probability theory. Now, these infinitesimalist approaches are approaches to probability theory in which you work not with a standard set of real numbers, but with the rich sets of real numbers that you get as a non-standard analysis by bringing in infinitesimals in the structure of the continuum. But, and so this seemed to open new possibilities for a defense of regularity by using infinitesimals in the range of the probability function. So the idea, what would be the solution to my problem about the 0, 1 interval? We can't give a standard value of probability which is different from 0 to a singleton. But if my range, and now we're going beyond Kolmogorov, because the range in Kolmogorov is always the real interval 0, 1. But if my range is enriched with infinitesimals, then I could give every singleton an infinitesimal value. That would preserve regularity, because an infinitesimal is different from 0, unless it's 0, but a positive infinitesimal. So that's the idea that people started exploring. And yet there was a reaction on the part of philosophers who thought that this way of saving regularity was not good. And so we have these articles by Williamson in 2007, by Isvaren in 2014, Hayek in 2011, which have claimed that the use of infinitesimals is not a satisfactory way of implementing regularity as a constraint on rational credences. For instance, Williamson provides a thought experiment with a countably infinite sequence of coin tosses and claims that even with infinitesimals at our disposals, the probability of such a sequence is 0. Meanwhile, Isvaren and Hayek argue that some of the key issues for orthodox Bayesianism, which is a particular position in formal epistemology, that is orthodox because it uses standard approaches to probability theory, and in particular, the notion of unconditional probability as basic. So probability for a standard Bayesian in the first place is a function that applies to a set. Non-standard would be to take the notion of conditional probability the probability of A given a set B as undefinable and primary. That's an approach that goes back to Popper, for instance, and it's done with what are called Popper functions. So what Isvar and Hayek claim is that the issues for orthodox Bayesianism that come up with regularity should not be solved by bringing in infinitesimals, but rather reconfiguring the probability theory in the style of Popper. Take as basic conditional probability and then define unconditional probabilities as a defined notion. And that gets you around some of the problems that you find in this literature. Now, what are those problems? Is that when you define conditional probability in terms of unconditional probability, the formula that you're going to have to use is going to require a product of probabilities on top divided by some probability at the bottom. And that probability at the bottom very often happens to be 0. And you don't want to divide by 0. So that is, and this has big consequences for revision update when you want to know, in the light of new experience, how you're going to revise your probability assignment, your credences. If you have these divisions by 0, that's a real issue. So this is the essence of this debate. I'm going to talk, since we had time, I went slowly because this stuff is a little tough to bring in. Maybe 10 minutes and I'll stop. So here is the way that Hayek described the situation with respect to bringing in infinitesimals. He said, I envisage a kind of arm race. We scotched regularity for real probability function by canvassing sufficiently large domain. In other words, we made regularity fail by taking domains that were large enough, making them uncountable. The friends of regularity, those who want to preserve that no possible event gets value 0, thought back, enriching their ranges. So making them hyperreal value. Hyperreal value here means simply introducing infinitesimals. And now you get this kind of arm race. The guy who wants to show failure of regularity says, you enriched your range, I'm going to enrich my domain again. I'm going to take something so big that failure of regularity is going to be guaranteed. The guy wants to say regularity says, okay, and then I'll enlarge my range. I'm going to get an hyper real valued range so I can preserve regularity. And so it goes. This is the arm race, where you try, player A tries to defeat regularity, and player B, by enlarging the ranges, try to save it. And so it goes. Some later day, Bernstein and Wattenberg, this is a reference to one of the very first articles in probability theory using non-standard methods from the 1970s, would need to keep coming up with constructions that would uphold regularity no matter how big the sample space gets. Presumably even with even richer fields of numbers to provide the values of the probability functions. So you see that in this even informal discussion, cardinality and infinitesimals and issues of regularity come together. We want to understand better exactly what is the mathematical nature of these relations. So in line with the dialectic outline so far, the formal results discussed in the literature on the topic can be roughly divided into two categories. On the one hand, we have existence theorems, which establish that under certain conditions on the sample space omega and the range of probabilities V, regular probability measures from P of omega to V can be constructed. So that's why they're existence theorems. Under certain conditions on the domain and the ranges, you can construct certain regular probability measures. On the other hand, impossibility theorems which identify conditions on omega and the range of probability under which there cannot be regular probability measures from P of omega into V. Okay, so these are the two branches corresponding basically to that arms race. Existence theorems, I can show you that if you grant me certain things, I will get a regular probability measure. And impossibility results saying, but if you are in these situations, you will never get a regular probability measure. So here is an example of an existence theorem. Take omega to be any infinite sample space. Then you can find an hyperreal, so a non-standard model, field R star of at most cardinality 2 to the omega and a regular probability measure from P of omega into R star. In other words, no matter how big omega is, say it has cardinality kappa, if you choose a range for your probabilities that has cardinality 2 to the kappa, you're going to be able to construct a regular measure on that set omega and its subsets. By contrast, the best impossibility results existing in the literature can be found in an article by Prass from 2013. And what Prass shows is that whenever omega is strictly larger in cardinality than the range of a probability measure, mu, then mu cannot be regular. In other words, pick omega, your sample space, large enough in cardinality so that it is larger in cardinality than the range of the probability measure, then you will never find a regular probability function from the subsets of omega into the range. Now, all of Prass's results in Prass 2013 require omega to be bigger in cardinality than the range of the probability function. We have no objections to see to these results. However, the failure of totality and regularity in many ordinary cases requires weaker cardinality assumptions than the one required by Prass's theorem. See, it requires that the domain be strictly larger in cardinality than the range. And we improve on this cardinality hypothesis by weakening it substantially. So here is our result. It's an improvement on Prass's impossibility theorem. When I speak of generalized probability function and generalized probability measure, we're using is set up. Don't worry about it. Just think of some generalized notion of range and probability. But for a generalized probability range, V less than or equal to plus and 0, and any set omega such that omega, the cardinality of omega, is greater than or equal to the range, there is no total V probability measure for omega. And this is a clear strengthening of Prass's result, because in his case, he needed the assumption that the cardinality of omega was strictly greater than the range. In our case, it is sufficient to be greater than or equal to the range. So we can also combine this novel impossibility theorem with existing theorems, such as those that I mentioned from Weber, and in particular, existence theorems coming from this literature on infinitesimal probability theory. This is very recent work from 2018, which has to do with the existence of certain type of probabilities theorem. Putting the two together, what we get is a full characterization of the situation under, just to make it simpler, we can state this result even without appealing to the generalized continuum hypothesis, but this is a very nice version. So this is what you get. If you have kappa to be a cardinal and omega is set, then there is a hyperreal field R of size kappa and a total regular and a total and regular finitely additive probability measure mu from the full power set of omega into R, if and only if the domain is strictly less than k. So this is a characterization, it's an if and only if about all the situations in which you can have regularity or not, depending on these cardinality assumptions. One final slide, because you might say at this point, wait, but what does all of this have to do with Zermelo's theorem? If I mentioned it yet, right? The key is in one essential observation, and I'm really going to skim through here, and it's the following, that the property of regularity for a finitely additive probability function. So finitely additive means that you're not asking for countable additivity, just finite additivity. The property of regularity turns out to be exactly identical, there is an if and only if, to the property of preserving part whole. And in probability theory, preserving part whole only means that if A is strictly included in B, the probability of A must be strictly less than the probability of B. Okay, so that's the bridge that connects the stuff on part whole and regularity. And here the difficult work was to, I'm just gonna skip this, the difficult work was to show the following. How do you, when you're dealing with Zermelo, you're taking a set X, you're looking at the power set of X, and then you have a function that sends you from the power set of X into X. But in probability theory, we're often in situations where we're not sending the power set of X into X. X, in fact, in Kolmogorov's case, is always the same. It's the interval 0, 1. And you have probability spaces in all kinds of situations where you're not taking the power set of 0, 1. So here, the real difficulty was to show that we could generalize Zermelo's theorem to a much broader framework in which we recover the possibility of having maps into 0, 1 to begin with, and then other sets as well, but from different subsets. And that possibility came through with basically, this is the proof of it. If you have a surjection of omega into any set X, in other words, to generalize the setup, you want something that doesn't force you to have the domain omega to be equal to the range. That's the case I gave you when I was sending things from the power set of 0, 1 into 0, 1. If I want to generalize, I want to send something from the power set of omega into either 0, 1 or even something else. Okay, well, the trick here is that because you're putting cardinality conditions on the domain, and you have to have the same cardinality at least for the domain and the range, that means that there is a surjection F taking you from omega to X. And now, with that, you do an inverse lifting, which is going to give you a map, basically, so you have this mu that takes you originally from the power set of omega into X. Then you have this surjection, and you take the inverse lifting of that, which takes you to P of X. When you compose the maps, what you have obtained is a Zermelo type map taking you from the power set of X into X. And then it will fail to preserve part whole, and automatically you will fail to preserve regularity because we've shown that regularity and part whole go together. So that is the, so this is a very nice, I think, a very nice application that kind of really generalizes the Zermelo's theorem in settings that did not seem initially to be subject to the same phenomenon. Okay, and with that, I think I conclude, and here are some of the recent things published in this area on probability theory. So, sorry I took too long, but I just wanted to Go despacito. All right, thank you so much.
Well, thank you, Paolo. After this, how can I say, dense and compact stuff in the presentation by you, surely there are many projections and many points that can be discussed. And well, we open the space for questions and for comments and for discussion in general. Yes, Guillermo.
Okay, thank you very much for the wonderful talk. I have maybe only one question. If I understood well, the diagnosis of the failure of Paolo principle has to do with infinite sets, in particular something like Cantorian infinite sets, where infinite is a projection of the sets into itself, and that caused the failure of Paolo's principles. And you can see that in abstraction principles, regularity, and so on. If that is okay, my question is, what's the role do you think have the power set operation? Because Zermelo theorem, power set operation is very important. So I think you can diagnose that the problem with Paolo's principles has to do in some way with power set operation instead of infinite sets as such.
So I disagree with the premise of your reasoning because this failure of power-whole preservation has nothing to do with infinity in particular. In fact, Zermelo's theorem, as stated, did not say let X be an infinite set. It said let X be any set and a function from the power set into the set itself. And if you just play around with finite sets and take a set with 3 elements, you're gonna get 8 subsets. And you can play around as much as you want with possible functions from those 8 subsets into 3 values, the 3 elements in the set, and you're never going to find a function that doesn't ruin the attempt to preserve part-whole. So I had to block the antecedent of your question. But it's good. I mean, all of this stuff. And I'm going to, kind of encourage you to ask questions you think might be, sort of basic, because it's very easy, and I've had this experience before, where even grasping the real meaning of Zermelo's theorem might cause problems, and I'm very happy to, kind of make it more clear. So don't be afraid if you feel like, oh, maybe I didn't quite get it, because it's tough stuff. I mean, it takes a while to see exactly what's going on.
Yes, Gabriela.
You talked about security argument at the beginning of your talk. Security
no, I didn't use the word security, but maybe something else. What did you hear?
Oh, that was.
When was it? At the very beginning?
Perhaps slide 3 or 4.
Let's go back. Okay. 2, 3. Maybe transfinite arguments? No, wasn't that? Or bad company arguments? Yeah, I'm not sure.
Okay. Maybe I look up or can.
Okay.
And then what is a sigma algebra?
Okay. A sigma algebra is an algebra of sets where you have negations, so complements. You have unions, and in particular you have countable unions. So it's a set closed under the following operations. For any set in the set, there is a complement of that set. And then for any countable number of sets in that set, there is also the union of them. And because you have both complement and union, you also get disjunction, intersection to be part of that. That's a signal. Yes.
Thank you for the presentation. I have two questions. I don't get very much why when we expand not the domain, the range.
Yeah.
Why we could have regularity. I didn't get that.
Okay. So let's go back to a simple example, the one with the darts. Okay. So we have the interval 0, 1. What we're doing is we want a probability function that tells me that every single element of that interval has some probability to be hit. Normally, we will ask even for uniformity because it's not clear why 1/2 should get a different probability than 3/4, say. Now, in the standard setup, right, Kolmogorov setup, you are forced to give probability 0 to each point. And the reason is simply that if you gave it any other value, when you take the sum for countable additivity, you're always going to go beyond 1. So you are forced to give it 0. Now, suppose your range is part of the interval 0, 1 in a non-standard model of analysis. What does that mean? It means that you have added these infinitesimal elements that are not 0 and yet are not standard finite real numbers, right? They sit in between 0 and any finite real number, but they're not 0. And so now you have the possibility of saying, oh, the value of my throwing a dart at the 0, 1 interval, now this is the classical 0, 1 interval, is going to be, because you're going from the domain to a range. So you're keeping the domain classical, but the range you're expanding. And so you're going to say, oh, all right, I'll take a singleton there, maybe the number 1/2, and I'm going to give it value infinitesimal. And now what's going to happen? That the standard argument that uses countable additivity is not going to take you beyond 1. Right? Because you're summing indivisibles. You're summing things that will never, they're not Archimedean quantities. They're not going to take you over 1. Of course, the clever thing of this approach is to show that there is something similar using infinitesimals that looks like countable additivity. And it's called, in fact, hypercountable additivity. And here's the beautiful thing, that points on the regular 0, 1 interval are assigned infinitesimals, and when you sum up all these infinitesimals, you get 1 as well. In other words, the total sum of the singletons is still going to be the full space, which is also something very nice. But you have been able to give a value to a singleton in the standard domain, which is a non-zero value. And that's saving regularity. Is that clear?
Yeah. But that preserves the Kolmogorov standard, the axioms that Kolmogorov.
No, it doesn't.
No.
No, it doesn't preserve So what you need now are, you see, now you need to study in detail how you move from a standard setup to a non-standard one. It can be done by simply, for instance, you can't preserve the notion of summing up over the natural numbers, because the natural numbers cannot be defined in the non-standard setup. They are what is called an external set. So you cannot do countable additivity. That's why I spoke of hyper-countable additivity in the new setup. But all of this has been studied, and you can get basically analog results to Kolmogorov's request but they're different from Kolmogorov's request. So hypercountable additivity is this formal analog in that setup. Of course, now you can ask, well, but that sounds like cheating, because you're giving values to things in the standard 0-1 interval by using a non-standard range. What's going to happen if you take as your range, as your domain, the entire non-standard interval 0-1, and you play the same game? Well, that's the war that Hayek was talking about. Then you're actually now increasing your domain and seeing how that's gonna go. And of course, in the case of 0-1, we are exactly in the case of the Zermelo's theorem, the most immediate application. So if I send the power set of the non-standard 0-1 into the non-standard 0-1, immediately I know that there is a failure power pole, because it's the very first, the most immediate application of Zermelo's theorem. I'm saying the power set of a set X into X itself. So you have to study now all these variations too, right? What happens if my domain is standard, but I'm sending on a non-standard set, or vice versa, and so on. In fact, the first application that one by Wattenberg that was named Bernstein, that was mentioned in one of the slides, that one was one in which one gave these non-standard values to the standard sets. So one started by assigning regular values, but keeping the domain standard, not enlarging it. Only the range was enlarged.
I have found my
Okay.
question here.
Yeah.
So shall we go to the slides where you presented Zermelo's theory?
Yeah. This one.
So let's see, next one. Next, and the last one is, I don't know where. Okay.
That's an interpretation.
Okay, I saw it and but.
Okay, another question or comment. Going to a more general and conceptual framework to discuss your wonderful talk with so many interesting things. You referred to the Russell paradox, and you said that Russell paradox, according to your research, were only one of many inconsistency consequences of that. I found very interesting to say that, in fact, it's a case of a more general, more general proofs that you showed. Well, in general, and going to the philosophical schools and or philosophical lines, so to say, your talk seems to be a critic, or your results should be a critic to neologisms.
Interesting, yeah.
What do you think about it, or what do you? So in all, and by the way, you. This is my first question. It's involved in all the problems where you work with second order logic and with general with set theory and what do you?
Well, you asked for it. So, very good question. So let me divide them into two parts. One is the one about second order logic, which I'm going to treat later. But let me start with the first, about where do I stand with respect to neologicism. So I'm not a believer in neologicism. I have the attitude that George Boulos had with respect to neologicism. I find it to be an interesting program. I made contributions to it, even though I tend to take kind of more the logician's point of view. I want to see what the limits might be of some, approaches or other. Now, when it comes to the issue of criticism, you have to distinguish two areas in which the debate has been going. One is the bad company objections, which I've already mentioned, and here my criticism, if there is one, has always been the following, that the way the literature on bad company objections has developed has been one of a great industry of, here is basic law 5, here is a killer argument, or what seems to be a killer argument, the neologicist responds, and then we move on. There is the next killer argument, there is the response, and so on. And I think that this kind of attitude, which is typical of a certain, kind of industry, is not to be defended. In particular, what I wanted to do was to say, wait, we have a great opportunity here to stop at level 1, the objection coming from basic law 5, and to ask, can we learn something about the roots of the contradictions, implicit or explicit, in even a basic principle like basic law 5. There is maybe an opportunity to learn, and I think I showed that the opportunity could have gone wasted if we kept this kind of industry of counterexamples, because by studying in particular the reasons for the contradiction of basic law 5, I think, I say it without trying to blow my own trumpet, shows that there is a huge generalization here to be looked at. And this is the generalization I presented. Any abstraction, not just basic law 5, any abstraction principle that preserves part whole is going to, get you into a contradiction. Now, that is the part having to do with bad company. But my stuff on bad company wasn't meant as an objection to neologicism. It was meant as an objection to the industry surrounding it, saying, look, take your time to actually study certain things because they might, yield interesting results. My objections to neologicism come from a different side, and this is what they're called good company objections. They're very different from the bad company. The bad company does what? Says, here is an abstraction principle that looks like Hume's principle, but gets us into trouble. Why would you want to preserve Hume's principle in the light of the fact that this principle, apparently innocuous, gets us into trouble? That's the standard bad company objection. My idea of a good company objection was, instead of looking at bad companions of Hume, I started looking for things that had the same virtues of Hume's principle. So to the point that they could not be distinguished from Hume's principle in terms of their epistemic achievement. So for instance, until I started working on this issue, Hume's principle was the only principle known from which you could derive the axioms of piano arithmetic. What I started doing was tweaking the equivalence relation, right? That one for Hume's principle says, if it only if the objects that fall under concept C are in one-to-one correspondence with the object that falls under D. And I said, well, let's start tweaking that. Let's say that we use one-to-one correspondence in the finite, and we use something else in the infinite, for instance, basic law 5. I still get an equivalence relation. I now define a new notion of number of, and I show that this principle generates the axioms of piano arithmetic. And I came up with infinitely many such things. So why good company? Because for all the things that the neologicists have looked at, trying to defend themselves, trying to defend Hume's principle against a bad company, all the things they came up with also apply to my principles. But now the objection is, well, if Hume's principle is true, is analytic in the sense of, then it's true. But how could it be true when I have this other infinite group of good principles that cannot be distinguished in terms of epistemic virtues? So they're all analytic and they're all true. But how is it possible? So the idea that there was one unique principle capturing the notion of number now is kind of, of course the dialectic continues. One could try, for instance, to show that what I call my good principles turn out to be, on account of some property we hadn't thought of yet, to be all bad principles. But no one has come up with anything of that sort, and I published my book in 2015, so that's already a good number of years with respect to this kind of profession that works as an industry, because usually you get objections within 1 or 2 years. So that's my objection to neologicism, that I don't see in what sense Hume's principle has any advantage over another myriad of possible principles that still generate exactly the axioms of second-order piano arithmetic. And there the discussion becomes rather complicated, because then what he really did, the objection, was to help distinguish various trends in neologicism that were often confused. And I'll just mention 2. One is a kind of novel approach that says, oh, it really doesn't matter if you came out with a zillion principles. All we needed was an a priori route to an abstraction principles that delivered second-order piano axioms. If you found 1 million of them, good for you. All we needed was one. Right? That's a very un-Fregean way of doing things, because Frege would have said, wait, but which one is the number 1? Is the one corresponding to Hume's principle, or the one corresponding to one of the millions that Mancosu came up with? So it's a very un-Fregean point of view. And the other thing that instead I think was part of much neologicism was instead that Hume's principle also counts as an analysis of an informal way of assigning number. And then the idea would be that something more must be appealed to in order to claim that Hume's principle really is the principle, and that the rest are defective in some way or other. For instance, they don't correspond to an intuitive notion of arithmetical thinking. And that's a very different position, because it says there is something more to Hume's principle than to any of these other versions. It makes these kind of abstraction principles responsible to some ordinary arithmetical thinking of sorts. And it could be an interesting defense of Hume's principle, but again, I haven't seen it. So, second-order logic, just to finish with your question. There the debate is huge, but everyone is in the same boat. So, if you have objections to second-order logic, as logic, Quinian style, and so on, then no one is going to survive here. Because then if you think second-order logic is mathematics, then nothing can be done, in the sense that you do need second-order logic to do the various derivations of the axioms and so on. So that kind of cuts across the spectrum. If you ask me, is second-order logic as opposed to mathematics, I think I'm going to disappoint you with the kind of pragmatic answer. Maybe again, it's the logician coming out. If you take it on board as logic, then you can claim certain things. If you don't, then you cannot. But it's interesting to know formally what can be done if you allow yourself second-order logic in these developments. So you can attack neologicism by saying you're taking on board second-order logic, but second-order logic is part of what needs to be justified because it's a part of mathematics, and it's not logic, and there have been attacks of this sort. That's not really what I do. I actually tend to keep second order logic in the realm of logic. I don't have much trouble with that.
Another question or comment? No, I wanted to make the following observation related to the second order logic. As far as it is not complete or does not have the properties of first order logic, you can get you can arrive to such inconsistencies and problems and so on. You perhaps it's related. You talk of security arguments. No, but you are in a, so to say, in a risky field. No? And it is very nice. So is science, so is life, so is no. I mean,
But,
you cannot arrive at these inconsistencies and
I see what you're saying, but I think that everyone's modus ponens is someone else's modus ponens, and here is why. What you now are contrasting are the bad properties of second order logic to the good properties of first order logic. But even this, I feel, is very conventional. I mean, take first order logic, right? It's unable to characterize any given structure semantically unless it's finite. So the natural numbers, we can't get them in first order logic. By contrast, in second order logic, the natural numbers are categorical, exactly what we want to capture. So compactness, which is true for first order logic, is exactly what gives rise to this plethora of different interpretations, right, for non-standard models and so on. Failure of compactness allows you not to do that in second order logic. So what I want to say is that depending on what your aims are, whether something is defective or not will depend on those aims. So I feel like, obviously there are good reasons for why logicians have decided to formalize theories in first order logic, but we know that there are lots of expressive limitations in first order logic. We can't say lots of things we would like to do, including the ones in second order, but not only. That's the reason for why we went to generalized quantifiers, the reason for why we went to modal logic, whatever. So, the moving to second order logic doesn't seem to me so problematic in the end. We have a good syntax. We know it's incomplete with respect to its intended model, but that doesn't stop us from writing down pretty good derivations in it. We just know that syntax will never be able to capture all the logical validities. How worse is that than knowing that piano arithmetic in first order allows you to write all the derivations you might really think of, although you know that there are true sentences of piano arithmetic that you'll never be able to capture with your theory of piano axioms. That's bad too. So I don't know. I think it's a kind of situation where no one is optimal, and I don't see second order logic as particularly problematic. It's not like we're dealing with something that is syntactically not well understood or even semantically. It's just that the properties it has.
Okay, it's
went on for a while.
Well, we thank you again for your presentation.
Thank you very much.